So before that, let me write the topics that I'm covering today on the board, which is pretty much continuation of curvilinear coordinates that we started last week on Thursday. Okay, so let me write the topics up here. Okay, so I'm continuing curvilinear coordinates today. I'm gonna start by a spherical coordinate. We had a definition. I'm gonna repeat that. We talked about the definition, how the coordinate is defined, and what parameters are used there. Next, I'm gonna look at the unit vectors, and we will look at infinitesimal elements, infinitesimal displacement, infinitesimal volume and surface. And that's going to be very interesting and very useful. And beyond that, we're going to look at the del operator. You know, we define del operator, we define divergence, gradient, and curl. So far in Cartesian coordinate where we have x, y, and z, right? If you move to a new different coordinate system, then the whole operator will change. Okay, so we're going to look at that and the mathematics of that. It's going to look a little more complicated, but at the end, this is something that if we have a problem with spherical symmetry or something like spheres, integration on a sphere, and so on, overall, it's going to make the situation a lot easier. Okay, I'm going to do one example, a simple example, but that's already going to tell you how much things can get simplified if we use a spherical coordinate for the right problem. Okay, and then I'm going to move on and define a different curvilinear coordinate, which is cylindrical coordinate, okay? And it has some similarity and some differences with the spherical coordinate. I'm going to repeat the same definitions, unit vectors, infinitesimal elements, and the del operator. And after that, we're going to move to the Dirac delta function, which is a very interesting topic and very relevant to electromagnetism that we will be dealing with this semester. Okay, so any question? You guys happy?
Yep.
Okay. So what was the idea behind the spherical coordinate? We define every point in a space based on 3 parameters. Okay, so if you are in 3-dimensional space, you always need 3 parameters to define, to locate any point in a space, right? So in Cartesian coordinates, we had x, y, z, right? So we had the axis like this, let's say x, y, and z. And we said in a spherical coordinate, what we do is that, let's say we have a point P here in space, okay? We define the position of P with three variables. R, which is this, that is the distance of the point to the origin. Okay, so this is simply the distance. Okay, and then we also look at the angle that R makes with the positive z-axis and measure it in this direction, and that is theta. Okay, so we have theta, which is polar angle, and then we have phi. Okay, so phi is the angle that projection of R on the xy plane makes with the positive x-axis. Okay, and phi is called azimuthal angle. Okay, so with these three set of parameters, we can uniquely position every point, locate every point in three-dimensional space. Okay, so now what is the relationship between x, y, z and r theta phi? Okay, so if you look at this, any position x, y, and z can be derived from the r, theta, and phi that we have. Okay, and that's going to be x. If you look at the x value here, it's going to be r times sine theta. Okay, so this length here is r times sine theta, and then multiplied by cosine of angle phi. So x is r sine theta cosine phi. Y is going to be r sine theta sine phi. Z is r cosine theta. Okay, so we get these three sets of conversion from r theta phi, the spherical coordinate, to the Cartesian coordinates. Okay, and then we also define the unit vectors, right? We said that unit vectors are in the direction that if we increase each of these variables, the point P is going to move in that direction. Okay, that means, let's say we increase R a little bit, what direction P is changing, right? The direction is going to be along the same length as R. Okay, so a vector pointing in that direction with a magnitude of 1, okay, is going to be our R hat. Sounds good? And how about theta? If we increase theta a little bit, what direction the point P is going to move? I'm asking you.
Towards the XY plane.
It's going to move
perpendicular.
as far as the XY plane. It's going to move down, right? So if we increase theta, the point P is going to move in a direction which is perpendicular to the R hat by pointing this way. Okay, so this is the theta hat. Okay, so if I want to show it in 3 dimensions, imagine my hand is R. R hat is going to be in this direction where the black marker is, okay? And then theta is a direction that if I increase, theta hat is in the direction, if I increase theta, it's going to move. So it's going to be in, it's hard to put this marker, but something like this. It's going to be in this direction. R hat and theta hat are always orthogonal to each other. Okay, so R hat is in this direction, theta hat is pointing down. Okay, how about phi hat? If we increase phi just a little bit, what it's going to do, we can easily imagine on the xy plane, right? We're going to have a vector that's pointing in, let me figure out what direction is the best to show. Something like this, in this direction. Okay, and if we compare direction of phi hat with R hat and theta hat, phi hat is orthogonal to both of them, okay? So we will have something like this, r hat in this direction, theta hat in this direction, and phi hat is going to be in a direction orthogonal to both of them, okay? So something like this, okay? R hat, theta hat, and phi hat. So it's going to move something like this. I hope this is helping you guys. Okay, so the unit vectors are always perpendicular to each other. Okay, and that's a very good thing, and that's actually what you want from the coordinate system. You want to end up having a unit vector that are always perpendicular to each other. And the advantage of that would be we can write any vector, okay, in terms of those unit vectors. If they are perpendicular to each other, pairwise orthogonal to each other, that's totally doable, okay? So with this set of r hat, theta hat, and phi hat, any vector like A, okay, can be broken down into three components: the r component times r hat plus a theta component times theta hat plus a phi component times phi hat, okay? And this is something we used to do in Cartesian coordinate as well, breaking down any vector into the components and do a lot of vector analysis using the components, okay? So something that makes spherical coordinate a little more complicated than Cartesian coordinate is that here the r hat, theta hat, and phi hat are not absolute constants, okay? If we compare with Cartesian coordinate, we had x hat, y hat, and z hat that were completely constant, never changing with anything position. But the unit vectors in the spherical coordinate move and change as you change your point. Okay, so the r hat itself is dependent on the theta and phi. Okay, depending on the angle, r hat can change. Okay. The size does not change, the magnitude does not change, it's always one, but the direction changes. And as you know, for vectors, if you keep the length the same, you change the direction, you are technically changing the vector. Okay, that's not a constant vector anymore. And this is what happens in a spherical coordinate. So we do have a set of unit vectors. They are orthogonal to each other, which is perfect. The size is always one, but the direction of the vectors depends on where is this point P in space. Okay, so for that reason, you got to be careful when you are doing calculations. Let's say if you are doing an integral or doing a derivative, these components, the unit vectors of a spherical coordinates, are not absolute constants. So you cannot easily take them out of an integral. Okay, so in the problems that we are dealing with, we will deal with a spherical coordinate. Depending on the context of the problem, it's going to be very easy to judge how to use the spherical coordinates unit vector and how to deal with it. Okay, so I don't want to confuse you too much, but giving you the warning that you got to be careful about the unit vectors and the constancy of the unit vectors. Magnitude is constant, direction is not constant. Sounds good? Any questions so far? You guys are being very quiet today. But I assume that this is more or less familiar and clear so far.
Yes.
Am I right?
Yes, sir.
Yeah.
Okay.
Yeah.
You know, whenever I see very quiet classroom, there's always two possibilities. One is the material is very clear, no one even wants to ask question. The other way is it's so complicated, the students can't even articulate the question. Okay. So hopefully we are on the easy side so far today. All right, so now the next thing I want to discuss is the infinitesimal elements in the polar coordinate. Okay, so for that, let me get rid of some of these things here because we don't need them. And then I'll have space to discuss all the details. Okay, now let's start with infinitesimal lengths. Okay, so in XYZ coordinate, we always use, we said in X direction, if we move a little bit, we use notify. the notation is going to be dx, okay? A small move in x direction, a small move in y direction is dy, and likewise for z, dz. And then for any move as a vector, we would write them dx, x hat plus dy, y hat plus dz, z hat is very small step that we are taking in a three-dimensional space to move from point 1 to point B, and assuming these are very close to each other, and that's an infinitesimal move, okay? So now we want to write dl in terms of the polar coordinates, r, theta, phi, the unit vectors of the r, theta, phi, and all other variables, okay? So now one difficulty is this. If you look at the spherical coordinate, the r distance has unit of length, okay? And that makes sense. If you look at theta and phi, they don't have any unit. They are angle and they don't have unit of length, okay? So we cannot simply write that a dl in a spherical coordinate is dr r hat plus d theta hat plus d phi phi. Okay, this does not quantify a move in a space because theta itself is an angle and does not really show a motion, a displacement. Okay, so this could be correct technically, but the two others don't even have unit of length. Okay, so this is not the right way of writing infinitesimal displacement in polar coordinates. Okay, now let's look more carefully. Okay. And let's imagine we do move P from one point to another point and try to figure out the position displacement, okay, in terms of R, dr, theta, d theta, phi, and d phi, okay. So now let's imagine we move it, we move point P only in radial direction. What happens? Theta remains constant, phi remains constant. What happens is that we just move one closer step, one small step in the r direction. Let me get rid of these unit vectors. Okay, so if we move one small step here with the distance dr, we move in the same direction, keeping theta and phi constant. Okay, so any move, let's say dl, in the r component can be written in terms of dr. Okay, because that little step is dr. Okay, so for the r component, it's relatively easy. You increase r a little bit, and your point moves. How much? The amount is going to be dr. Okay. Now imagine you change theta a little bit. Okay, so you add d theta to theta. Okay, what happens? Theta moves a little bit, and the point P moves down here. Okay, how much is this displacement? Is it d theta? Can't be d theta, okay, because d theta is angle. If r is a huge number, you change the angle by d theta and it's going to be a bigger move, okay? So the length here, okay, the length here is going to be d theta times radius, okay? So the displacement is going to be d theta times r, okay? So any small infinitesimal displacement in only theta direction can be written as r times d theta. Make sense? Yes. And how about phi? If we move phi a little bit, okay, if we add d phi to it, how much displacement we will have for P? For the phi, it's easy to only look at the xy plane. If we change phi a little bit, we're going to have a displacement in this direction, okay? And the amount of displacement is going to be d phi, sorry. The amount is going to be d phi, okay, times this length, which is r sine theta. Okay, so any small displacement in the phi hat direction is going to be r sine theta d phi. Okay, so we have this set of infinitesimal displacement. each of them is written with the assumption that the two others remain constant and one parameter changes. We will have dr displacement if we keep theta and phi constant and change r. We will have r d theta displacement if we keep r and phi constant and only change theta. We will have r sine theta d phi in the case that we keep r and theta constant and only choose phi. Okay. And the direction of each of these displacement is going to be actually in the same direction of the unit vector. So this is in the same direction of r hat, this is in the same direction of theta hat, and this is in the same direction of phi hat, the unit vectors. Okay. So looking at this infinitesimal displacement and looking at the fact that they are in the same direction of the unit vectors, every infinitesimal displacement in polar coordinate, in a spherical coordinate, can be written as dr r hat for the r component plus r d theta hat plus r sine theta d phi times phi hat, which is the phi component of the displacement. Okay, so this is now the correct general form for the displacement in the spherical coordinate. Any question? You guys happy? Let me check the chat messages. No chat message here. Okay.
So that's assuming everything stays
I
constant?
can't hear. Let me increase my volume here. Okay, now you can ask.
So that is assuming everything else except the variable that is changing stays constant, right?
Okay, so when I wrote this set of the equations, right, I assume one of them is changing, the two others are constant, okay? And then I looked at the displacement and I said they are in the direction of the unit vectors, okay, as they should be, okay? So this is written with that assumption, but this DL actually includes any random displacement in all directions combined. The fact that we have r hat, theta hat, and phi hat component means it covers any motion, any displacement, infinitesimal displacement in combination of directions. Okay, this is pretty general for a spherical coordinate. Clear?
Yeah, yeah.
Excellent. Okay. So the next thing we're going to look at are, so this is infinitesimal displacement. We're going to look at infinitesimal volume and area as well. Okay, and I would say everything starts from right here. As soon as you have this one, you can easily derive the displacement for the infinitesimal elements for volume and area as well. All right, so shall we do that part together? Okay, so I'm gonna keep asking you guys questions and you try to answer. Okay, so how about I first write and explain what we do in Cartesian coordinate and we try to expand that for the spherical coordinate. Does that make sense? Okay,
Yes.
and that's easy. Okay, so for the Cartesian coordinate, we said we have this combination that defines infinitesimal displacement. Okay, so we have dx and x hat, dy in y hat, and dz in z hat. Okay, so now if you want to write infinitesimal volume using a spherical, using Cartesian coordinate, okay, what we do is that we consider this as a cube, okay, a small cube with the length of each side being dx, dy, and dz, okay, and the volume of such a sphere, such cube is going to be dx, dy, dz, okay, and this is infinitesimal volume in Cartesian coordinates, okay. So we're going to do the same thing now for the spherical coordinate, okay. So the type of cube we want to assume in a spherical coordinate is not quite like this. It's actually a cube that can be formed at the end of this R. So if I delete everything here, okay, so it's going to be a cube like in this direction. This is one lens, this is another lens, this is another one. Okay, so this is going to be one side of the cube, and if we increase phi, we're going to extend the cube, let's say in this direction. Okay, so the volume of this is actually the d tau that we want to figure out in a spherical coordinate. Okay, so now you guys tell me what are the lengths of these sides. Okay, what is this length here? And a hint is that it should be either this one or this one or this one. Okay, this length here is in the direction of
dr r hat.
r hat. So this length is going to be actually our dr r hat, or simply the length is going to be dr. Okay. What is this length here? That is in the direction of
Theta hat.
theta hat. And the length should be rd theta. Is that correct?
Yeah.
Yes? Anyone else? Okay, so this is going to be rd theta. Okay. And what is this length up here?
R sine theta d
That's
phi.
the phi hat. So
phi
this is
direct
r sine theta d phi. So this is r sine theta d phi. Okay, so we have a cube with those lenses. Technically, dr times r d theta times r sine theta d phi. Correct? And the better way of writing this is r square sine theta dr d theta d phi. Okay, and this is infinitesimal volume using spherical coordinates. Okay, so you see the approach, right? You just look at this geometrically, what kind of a small volume we have, and you measure the length, and you just calculate the volume. Okay, so this is d theta. Any question?
I was just wondering, why did you do this is a small question, but why did you do d theta instead of like d, or because you say we're looking for volume, right?
Yes.
Okay.
If you look at the volume, okay, at the end you have all of the coordinates, dr, d theta, d phi for sure. Okay.
Oh, I see.
If you work in polar, spherical, or cylindrical coordinate, what else you need is some prefactors that bring infinitesimal angular displacement into infinitesimal lengths. Okay, that's why here for the r we only have dr, but for theta we have rd theta. And if you look at this, the unit of this is going to be length. For the other direction, phi, we have d phi times r sine theta. Again, something that made the unit of this being length. Right? So for volume, we need length times length times length. And you need to make sure you are actually using the right displacement for each direction. Okay? D theta itself is not length. D phi is not length. It has to be multiplied by the length that the change of the angle makes it actual displacement. Okay, sounds good. You have seen these things in other courses too, in calculus too, right? Okay, so I want to make sure that you have all the tools that you need for the rest of this course. That's why I'm going over all the steps of this. All right, so far so good. Any more questions?
Nope.
No? Okay. So I think, okay, the next thing I want to discuss is the next thing I want to discuss is infinitesimal area. Okay, so if we are in Cartesian coordinate, okay, let's say if you want to measure very small volume, first of all, it depends which volume we are looking at. Okay, if you look at this, sorry, it depends what surface area we are looking at. If you look at this surface area, what is the area? We have dy here, we have dz here. I'm writing on the top. dA can be dz times dy. Okay. If we look at another area with, let's say now this blue shade. Okay. So the blue shade is going to be dA equals dx times dz. Okay. So depending on what area we are choosing and what surface we are integrating on, there are different options for the surface, infinitesimal surface. Okay. Now, if you look at the polar coordinate, the spherical coordinate, there are different ways that we can identify very small area. Okay. One way is looking at this area. I'm gonna put a blue shade on top of this. Is this clear on your screen? Which side is blue? Yes? Okay. So what is the area of this blue side here? I'm going to call that dA1. I'm going to write that with blue.
So r sine theta d theta times r d theta?
R sine theta d theta times r d theta.
R d theta.
So let's look at that. On one side we have r d theta, and on the other side we have r sine theta d phi. Okay, so this is correct. R sine theta d phi times r d theta. Okay, so this is the correct form. If I write it in a more concise way, it's going to be R2 sine theta d phi d theta. Okay, and that has two angles, okay, and r squared. The unit, always check the unit. It should be length times 2, okay, length squared. Okay, so this area, this kind of element is very useful if, let's say, you are trying to measure the area of a volume, okay? So because the way this area is pointing, the r remains constant and we are changing the angles d phi and d theta, okay? And the surface of the sphere is a surface that r is always constant and we are only changing the theta and phi, the polar and azimuthal angles, okay? So if you are doing an integration to find the area of a volume, area of a sphere, right, you need to have this sort of infinitesimal surface area, okay? Sometimes you need a different one because let's say you are measuring something different, let's say cross-section of the sphere or something like that, then this area is useful. My red is almost out. Let me try another marker. Yeah. Sometimes this area is useful, right? And that is really in the cross-section of a sphere and not on the surface of a sphere, okay? And I'm gonna call that dA2, I'm gonna write that with red. What is this area? In one direction we have dr, in the other direction we have r d theta, okay? So this is area with r squared times, we have dr and r d theta, we have, sorry, don't have a square here. We have r d theta times dr, okay? So this is another area, okay? And if you look at this, it only has theta and r, okay? That means the phi is being constant if we move on this surface, it's the red one, okay? The phi is constant, but r is changing, theta is changing, okay? And another area could be right on the top of this, and that's an angle that where theta is kept constant. Okay, on the top, I'm going to write that with black, dA3. From one side, we have dr. From the other side, we have r sine theta d phi. Okay, so again, it's going to be r sine theta d phi times dr. Okay. So surface area, depending on what direction we are moving and what is the surface of interest, relative to the coordinate system, we will have three different options. Okay, and that's what you figure out when you are actually dealing with the actual context of the problem. Okay, does it make sense? Everything here?
Yeah.
Yes. Okay. So the next topic I want to discuss is the del operator. Okay, and for that, let me get rid of, you know what? I'm going to get rid of everything here. All right, so in a very similar way that we saw any infinitesimal displacement had different sort of a mathematical formulation in a spherical coordinate, the del operator will have a different type of mathematical shape and formulation, okay? In Cartesian coordinate, we define del operator as d over dx times x hat plus partial over partial y times y hat plus partial over partial z hat. Okay, so we had this sort of definition for the del operator, and this is correct in Cartesian coordinates. Okay, and if we move on to a spherical coordinate, technically we are moving from x, y, z to r theta phi, okay? And then there's always a relationship that I wrote between x and r, okay? If we want to write all these terms in terms of the polar coordinates, basically what we need to use is the chain rule, okay? So any d over dx, okay, any variable like that can be written in terms of d over, let's say dr, which is times dr over d, sorry. Over dx plus d over d theta times d theta over dx plus d over d phi times d phi over dx. Okay. So these sums, the parentheses can be calculated because r, theta, and phi can be written in terms of x, y, z. Okay. And then any function which is written in terms of the r, theta, phi, we can use this chain rule to expand each of these derivatives. Okay. So here what we are doing is expanding the derivative using chain rule for the derivative. Derivatives, okay. And then we have x hat, y hat, and z hat, okay. And x hat, y hat, and z hat can also be written in terms of r sine theta, r theta, and phi, okay. So the basic idea at the end is this: if we have a function t in terms of x, y, z, we can use the Cartesian coordinate, okay. But if we have the same function in terms of r, theta, and phi, where we cannot directly get this derivative, then what we should do is that we should use this chain. Okay, so the expansion of this conceptually is not difficult. Okay, you will have r in terms of x, theta in terms of x, phi in terms of x, and then you can calculate this partial derivative. And any function at the end, you can take the derivative with respect to r, theta, and phi instead of x. X hat, y hat, and z hat can also be written in terms of the r, theta, and phi. The only complication is that it's going to be very, very lengthy and long. Okay, I don't even think in the appendix of the book they have done that. Okay, but the good news is that you do it once, and then you will have a definition of the del operator, whether being gradient or divergence or curl, in terms of the polar coordinates. And once you have that, you can use it forever. Okay. The formulation, the equation may not look very simple, but the thing is that people do it once, and in fact, this is one of those things that you can find right on the cover of your book. Okay, it's not something you need to memorize. Okay, I'm just telling you what the approach should be to come up with those, and what I want to do next, I'm just going to give it to you what the gradient, divergence, and curl look like in a spherical coordinate. Okay, and then from that on, you don't really never need to drive that. It's good to know conceptually why you need that, but then you can look at the cover of the book and you can always find it. Okay, you can always Google as well, like divergence in a spherical coordinate, and it's going to come up very quick for you. Okay, so this is one of those one-time things once person does, and then you can follow it. Okay, of course it's important to and it's important to know the concept. Okay, and it's important to know how you need to drive that if you need to, but you don't need to memorize it. Okay. Okay, you know what? Let me, on my screen, my email is open and I'm getting emails one after another, and that's distracting. Let's turn that off. Okay. So, any question? Okay, so what I want to do next is that I want to start by the gradient and just give it to you what the gradient looks like in a spherical coordinate, and then move on to divergence and curl, and then wrap it up. Okay, so let's clear this one. So if we have, again, function t, now in terms of r, theta, and phi, the gradient of the t is dt dr times r hat. Okay, so as you see, the r component is very similar to the components that we had, to the terms that we had for Cartesian coordinates. It's going to be partial derivative of t with respect to r times r hat, but for the angular component, it's going to look different because they have an additional length. So for theta term, it's dt over d theta times theta hat. And for the azimuthal angle, we have r sine theta dt over d theta times phi hat. Okay, so this is a gradient in a spherical coordinate. The main difference that you see is that we don't have only the derivative. We don't have only the derivative and unit vector. We have some prefactor here as well. Okay. And for gradient and divergence, when you become expert, it's easy to guess what these prefactors should be by just imagining that the infinitesimal cube you have is in the r direction, okay, and looking at the displacement being dr, r d theta, and r sine theta d phi. Okay, and then map it to x, y, and z. Okay, but
Professor?
I don't expect you to do that. What I want you is that to understand this and then follow this equation whenever you need it to take the derivative, gradient, or divergence and whatnot. Okay.
The last one is supposed to be dt over d phi, right?
Yes, you're right. This is fine. Thank you. Cool. Okay, so this is a gradient on a scalar function. Then we can have divergence. Okay. And that's going to be 1 over r squared d over dr r2vr. R sine theta d over d theta times sine theta d theta. Okay, and these are terms for the divergence. The curl becomes more complicated, and I'm just writing a determinant for you guys to see how the curl looks like. And the direction of the unit vectors on the top are r hat, theta hat, phi hat, but then we have other terms, r2 sine theta here, theta, r sine theta, derivatives here, and then we got v. Okay, so this is going to be basically a huge determinant of this matrix. Okay, so if you compare it with Cartesian coordinate, we used to have x, y, y hat, so x hat, y hat, and z hat here, but now we have r hat, some other terms, theta hat, other terms, as well as the phi hat, and then here are the derivatives, very similar to the Cartesian coordinates. And in the last one, we have VR, but here also we have some prefactors for the theta component and phi component of the vector. Okay. And again, these things, you don't really need to memorize. You just need to understand it and know where you can access them. Okay. So I don't want you to get scared by the complex look of this equation. Make sense? Okay. Any question?
Nope.
No? Okay. So if there's no question, I think it's time to move on to cylindrical coordinates. Okay. And I'm going to pretty much repeat similar things, but much faster for cylindrical coordinates. Okay. So cylindrical coordinate is in a way something between a spherical coordinate and Cartesian coordinate, in the sense that x and y components are written in terms of the length and angle, but the z component remains the same. Okay, so in a spherical coordinate, we have one length. In a cylindrical coordinate, we have one length, one angle, and z. And z is exactly the same z that we had in Cartesian coordinates. Okay, so let me first draw the geometry, and then we define the infinitesimal length and displacement and so on. Okay. Okay, so imagine we have this XYZ Cartesian coordinate, and then we have a point P here, okay? And one way to locate this point P is first looking at the projection of the position on the XY plane. So it's going to be something like this. Okay, and then we have this angle phi. Okay, and then instead of looking at the distance from the origin, now what we do is that we look at the distance from the z-axis. Okay, so we first look at this distance, and I'm going to call that S. Okay, S is how far this point is from z-axis, and this is a 90-degree angle. Okay, and one more thing is I look at the actual z position. So this is going to be z, okay? And the last thing is that what angle this projection makes with the positive x-axis, phi, okay? So now in this coordinate, we have S as a distance from the axis, we have phi, and we have z, okay? So with this combination, we can locate any point in this space. Sounds good? And then we can write x, y, z really in terms of the s, phi, and z. So if we want to write x is going to be s times cosine phi hat. Cosine phi. So x is s times cos phi. Y is s times sine phi. And z is going to be z. Okay. So this is a set of equation to move from cylindrical coordinates to Cartesian coordinates. Z is exactly the same z. X and y are written in terms of the s, distance from the axis, and phi, which is the angle it makes with the positive x-axis. Sounds good? Okay, so as long as you are defining something on the xy plane, it looks very similar to a spherical coordinate. And as soon as you have any displacement on the z-axis, it's very similar to Cartesian coordinate. Okay, I want to put it that way. And then, now let's look at the unit vectors. Okay, so 3 unit vectors, one of them is a unit vector in the direction of s, and the same way we discussed with a spherical coordinate, the unit vector should be in the direction that if we increase s, the point P is going to move in that direction. Okay, so that means the s hat should be right in the same direction, and this is s hat. Okay, and then the other parameter we had was phi. If we increase phi, okay, it's going to give us a unit vector in this direction, or if I want to put it up there, it's going to be in this direction. So this is phi hat. And s hat and phi hat are perpendicular to each other. Okay. Another unit vector should be in the direction of third variable, which is z, and that z is exactly like z hat in Cartesian coordinate. So this is z hat, and it's pointing up. Again, these are unit vectors that are mutually orthogonal to each other, and that's what we really like for a coordinate system. We want unit vectors be orthogonal so that any other vector can be written in terms of the unit vectors. Similar to spherical coordinate, the unit vectors of s hat and phi hat are not absolute constants. If you change the position of P, if you change the angle, the direction of s hat and phi hat is going to change. And they are only a function of the phi, the angle. So far, so good? Any question? All right. So, shall we move on and define infinitesimal elements? Okay. So I assume that your mindset is now very, very well ready to do this, because we did that for spherical coordinate, and it's going to be very similar. Okay. So any displacement dl in s direction. Okay, that means if we keep z and phi constant and only change s by a small value ds, what kind of displacement we will have? it's going to be, the point is going to move a little bit in the S hat direction, and the amount of displacement is going to be ds. Okay, and that's very similar to dr in a spherical coordinate. Now, displacement, if we change phi a little bit, change it from phi to phi plus d phi, we will have a displacement in this direction. The amount of displacement is going to be d phi times s, right? So d phi itself is an angle, but if we multiply by s, that's going to tell us what is the amount of move, okay? And then the displacement in the z direction is going to be dz, very similar to Cartesian coordinates. So we have this set of displacement in each direction. Of course, the ds is in the direction of s hat, s d phi is in the direction of phi hat, and dz is in the direction of z hat. Okay, so based on this, any infinitesimal displacement can be written in terms of 3 terms in each unit vector, and that's going to be ds times s hat plus s d phi times phi hat plus dz times z hat. Looks good? Okay, so starting from this, now we can write infinitesimal volume and surface, okay, and area, right? So d tau, infinitesimal volume, how can we write that? From the experience from spherical coordinate, right? One thing we can do is looking at each of these displacement terms in each direction, okay? So technically we are writing the volume of such cube here. I'm gonna first try it up here. A cube that has length like this, and another direction is in the direction of s, and the other direction is in the direction of phi hat, something like this. Oh my God, that's not beautiful. Okay, something like this, with the length being this side being ds, this side being s d phi, and this side being dz. Okay, so any d theta can be written as s ds d phi dz. Okay, so we have ds, which is unit of length, we have dz, which is unit of length, we have d phi, which is not unit of length, but multiplied by s, it's going to be unit of length again. So it has unit of length to the power of 3, as it should have, right? Okay, is it clear, everyone? If not, it's good time to stop me and ask questions. I don't see any chat messages either. Okay. So let me make this a little more. Okay. So now with these unit lengths, we can easily move on and write infinitesimal area, right? And again, it depends on which area we are looking at, okay? So let's color code this again. If we look at this area on the side, okay, so what is dA for the red shade here? We have s d phi on the one side and dz on the other side, so we're going to get s d phi dz, okay? And then another side is going to be this side, the blue shade, and dA2 is going to be S d phi times ds. And then the other side, the black shade, dA3 is ds times dz. Okay. So these are three infinitesimal area that we can have in cylindrical coordinates. Sounds good? Okay.
Okay.
So, and then the next thing is the del operator. Again, very similar to spherical coordinate, we will have a different set of del operators, gradient, curl, divergence, also Laplacian. The point is that conceptually they are the same, but now we are using a different coordinate system and different variables. Okay, this looks again different from a spherical coordinate. Okay, what I want to do, I'm just going to write them for you. Okay, and the address is the cover of the textbook. You have all the equations here. If you need to use them, we just go there and we look at them and use them. Okay, so let me. So pretty much I'm copy pasting from the textbook, this part. Okay, let me erase this part. Okay, so these are gradient, divergence, and curl using spherical coordinates. Okay, I guess curl can be written in terms of a determinant as well. Okay, but the textbook wrote it in terms of the algebraic terms like this. Okay, so with this, I think we concluded the discussion on the cylindrical coordinate as well. Okay, and the next topic is the Dirac delta function, which is a beautiful, beautiful concept. Okay, so we have like a few minutes. What I'm going to do is that I want to introduce the Dirac delta function very briefly, and then the actual discussion is going to happen on Thursday this week, the day after tomorrow. Okay, any questions so far? Any question on the spherical or cylindrical coordinate? We are kind of wrapping up that topic now.
Yeah. In what chapter I can find these definitions?
Which definitions?
The
The
delta
definitions,
operator and
the del product, the del
yeah,
operators?
yeah. So I can write them
Okay,
down.
so these are in chapter 1. Okay, so that's taught in chapter 1. But then if you go to so this is the textbook. Okay, this is right on the cover. Okay, so if I bring it closer to camera, you see it right. So right on the cover, you have this Cartesian, spherical, and cylindrical coordinates with all the definition of gradient, divergence, and curve. Okay, so this is right the very first page of the book. Sounds good? Okay.
Thank you.
So, so I'm going to stop the curvilinear coordinate discussion and move on to Dirac delta function. Okay, so imagine something like this. Imagine a function that one-dimensional function for now, okay, and that has a peak. Okay, and let's say this function fx, oh, you know what, let's just set it as delta x. Okay, imagine this is a function with a peak. Okay, and what I do is this. I define it within the constraint that if I integrate delta x dx, the integral from minus infinity to positive infinity be 1. Okay, so we have this function delta x with the condition that we integrate it from minus infinity to positive infinity, the value of that integral is 1. Okay, and that means the area under this graph is 1. Okay, and the shape of this, imagine it has a peak like at x equals 0, which is very steep, and at the rest, if you go away from 0, it's going to be very small. Okay, now imagine I push this function to the limit. Okay, and by that I mean I push it from the sides. Okay, from the left and right, I push it in a way that I make it narrower and narrower. Okay, and as I make it narrow, I try to keep the area still stay at 1. That means that if I push it up from the sides, I should increase the value of the peak. Okay, the narrower it is, the higher the peak should be. Okay, in the limit that I push it really, really narrow in a way that as soon as you move from x equals 0, the value of function drop to 0 very, very rapidly, then that requires that the value of the peak right here be almost infinity, because I want to maintain the condition that the integral of the function, the area under the graph, stays 1. Okay, so if you make it super narrow, there is no other option than make it also super tall. Okay, so in the very, very limit of function dropping to 0, as soon as we move away from the axis, then we will have this definition, okay, that the value of the function always is 0 if we are away from x equals 0, and the value of the function becomes infinity if we are at 0. Okay, so this condition happens if we want to maintain this limit as well. Okay, so it's a very weird function. Okay, it's a very weird function. It is always 0, okay, always 0 except right at x equals 0. And the value at that point is infinity. Okay, But we need to do that if we want to maintain this condition. So the integral condition that defines the area under graph is staying at 1. And the limits here, that x being 0 and non-zero right at the center, actually defines the delta function. It's a one-dimensional delta function. So why is it useful? This is such a weird function, right? Why is it useful? Because it really has an application in physics and probably in mathematics as well, okay? And this is very useful function, especially it's used a lot within the integrals. It's used to define, in our course, the point charge, okay? The point charge, we will talk a lot in electromagnetism. The point charge is technically a delta function, in the sense that we have charge distribution only confined at a very, very tiny single point. Okay, so that's like delta function. We don't have charge distribution everywhere except at one point, okay? And that charge distribution creates electric field, okay? And in order to create electric field, then you need to have such integration becoming a finite factor, okay? So I'm gonna stop here. I just introduced this one. On Thursday, I'm gonna start not from here, I'm gonna start from the divergence of various special function and relate the divergence to the definition of Dirac delta function. Okay. Okay, so for now I want to stop here. I want to tell you something. So the quiz will be next week on Thursday. Okay. Hoping that I will finish chapter 1 on Thursday. I think that's gonna happen. Okay. So the quiz will be next week on Thursday, and to practice one more round of test of the critic platform, today around noon, I want to post the quiz again. Again, the practice quiz is the same practice that we did last time, but I want everyone, okay, every single person participate. Last time, 3 students did not participate, so I want every single person participate. I want you submit 2 things. One of them is your paperwork. Could be exactly the previous one, okay, if you still have it. And the other thing is a file, is a text file, which is one single link to your video. So video could be on Dropbox, could be on YouTube, or could be on anywhere else, okay? So a link for your video, and I want you to move on, and then you do your review and feedback of the reviews as well, okay? And actually, I'm gonna go to the website and read all of them as well. So around noon, I'm gonna post it. You will have 12 hours to create your submission, and then you will have 1 day to evaluate and do the rest. Okay, so I want everyone to participate, and then we will discuss on Thursday if there's any problems still with the platform. Sounds good? Any question? And again, I want everyone to get started on the assignments as well. If you start early, it's gonna be easy for you, okay? If you start late, you will see it's a lot of things. If you do 2, 3 a day, it's gonna be easily be done, okay? And as you do it, it's also a practice and exercise, makes you ready for the quiz as well, okay? So you are catching 2 birds with 1 stone. Sounds good? Okay, everyone, enjoy the rest of your day and see you on Thursday.
Thank you, Professor.
I will be in touch.
Thank you very much,
email.
Professor.
Okay, I will be in touch with email about the quiz, okay?
Thank you, Professor.
See you guys
Thank you very much, Professor.
Bye.
Thank you.